Hello, can you hear me?
Perfect.
Okay, great. Hi, I'm Benjamin Giblin. I'm a research fellow at the University of Edinburgh. This talk is all about using machine learning to get cosmological information out of data that's inaccessible to standard theoretical models. So here I'm showing you some real cosmological data. It's the projected large-scale structure of the universe inferred from the gravitational lensing signal of galaxies imaged by the Kilo Degree Survey. So this is a gold mine of cosmological information, much of which can't be extracted with two-point functions because this density distribution is non-Gaussian. So the statistic that we use to extract more information from this data is quite simple. It's simply the probability density function of these maps, how many pixels there are of a given density. So this is sensitive to cosmological parameters. You can see the variation of this statistic with the mass energy density omega m and the amplitude of density fluctuations sigma 8 in the upper and lower panels here. This is the point where those who are paying attention will say, wait a minute, you said this density was non-Gaussian and these PDFs look pretty Gaussian to me. And that's right, because these were measured from simple Gaussian simulations. To constrain the cosmology of the real universe, we need something more sophisticated, and we use the CosmoSlix M-body simulations. These are weak lensing mocks, dark matter only, that comprise a range of cosmological parameters. You can see that they vary in omega m, the strength of clustering parameter S8, the Hubble parameter, and W0 here. And this is where machine learning comes in, because we use an emulator that uses Gaussian process regression to interpolate between these points. We measure our statistics from these simulations, and then we have a numerical model capable of making a prediction for our statistic as a function of arbitrary values of these parameters. And that we can plug that into an MCMC sampler and get cosmological constraints. So these are the constraints for some simulated data tailored to match the specifications expected of Euclid. These are the constraints on omega m, S8, and W0. In black, you have the constraints from the standard approach, the correlation function. And then in orange, you have the constraints from this new statistic, which is the PDF of these density maps. Also shown in dashed pink is the combination of the correlation function and the PDF, and that's identical to the orange contour, which tells you the PDF has absolutely all of the information that's in the correlation function and more. So it's an 90% improvement in cosmological precision. If you want to know more about this, please look at this paper, or better yet, just come and talk to me. Thank you very much.
Thank you.